So in this video we're going to calculate the homology of the torus. Okay, so here's a picture of the torus. Okay, so there you go, there's a torus. But what we've done here is we've constructed this in the way that you should be familiar with from the knots and surfaces course. We take a square, and it's got two opposite edges marked here in red and two opposite edges marked in green. And to start with, we just glue the two red edges together. That gives us a cylinder. And then we glue the two ends of the cylinder together. Those were the kind of original green edges of the square, and that gives us this torus. Okay, so so our torus T, as we said here, this is we take a square, and we're going to glue this edge here to this edge here. This edge we're going to call V, and this edge here is going to be the same when everything's wrapped up. That's going to be the same as this edge here, and that we're going to call W. So this is our torus, and we want to calculate its homology. So we're going to divide it in the usual way into two open sets U and V, and then do the Myvia torus sequence. So we're going to have our U is what we get by kind of cutting a hole in the middle. And of course this is supposed to be interpreted with the same gluing still. Okay. Whereas our V, okay, so our V is the just drawn in the outline, but the outline is not part of V. It's just this shaded bit in the middle that's V. Okay, and so U intersect V. We've taken, here was our V, and then because we're taking the intersection, we kind of we're losing the hole in the middle again. So there's our U intersect V. Okay, so we can calculate. So our torus is T is the union of U with V, and so we can use the Myvia torus sequence to calculate the homology. For that, of course, we need to understand what are the homology of these pieces. Okay. So this V, of course, is contractible. Right? It's just basically homeomorphic to an open square, and so the homology of V, we just get a Z in degree 0, and then zeros. Whereas this is homotopy equivalent to the circle S1. Okay. So the homology of U intersect V, you've got a Z in degree 0, and then we've got a Z again in degree 1. We'll just mark in a generator. Okay, so here's a path here, which I'm going to call I'm going to call this path U. This runs around the circle, and so by our previous discussion of how the homology of the circle works, you've just got U generates your H1, and everything else, all the remaining homology groups are 0. But so that's the homology of U intersect V and the homology of V. Then we need to understand about the homology of this U. Okay, so here we took our torus and we kind of cut a hole in the middle. Okay, so and if you look at it sort of in the wrapped up case, by cutting a hole in the middle, we get a thing like this. And the homeomorphism type doesn't depend on the exact size of the hole. So it becomes clearer if we make the hole bigger, push it out towards the edge. Now what you can see is that after wrapping this up, what you've got is just like these two bands. Okay, you've got the red edge on the top and the red edge on the bottom. So this has kind of got a fringe on one side, and this has got a fringe on the other side. And when you connect them together, you see you've got fringes on both sides of the red arc, forming this kind of band in the middle there. And similarly, it's got blue here, and you kind of got a fringe on one side of the blue edge and a fringe on the other side of the blue edge. And when you wrap them up, you kind of get the blue edge in the middle fringes on either side. So you've got these two bands like this, which intersect like that. And so it's actually homeomorphic. It stays homeomorphic to the same thing, however thin the band gets, as long as it's not completely collapsed down to zero. And then if you collapse it down to zero, well, now we've got a space that's homotopy equivalent to the original U, but not homeomorphic to it anymore. But anyway, in this one here, is a union of two circles meeting a single point. That's a space that we called W, W2 in the last video. Or you could calculate the homology of the sort of fatter thing in the same way. But either way you see it, we get the homology of this U. You get kind of it's connected, so the H0 is just Z, and then you've got these two loops, each of which contributes a copy of Z to H1. So we've got a Z in degree 0 and a Z squared in degree 1. Yeah, and remember, so the homology of U. Okay, you've got a Z in degree 0, as we said, and then you get Z's in degree 1, but you get one of them is generated by V. I mean, V is a loop. Once you've wrapped everything up, V is a loop, and so it represents a homology class, and that's one of the generators, and the other generator is your W. Okay. Okay. So, and remember the way the Myvia-Torus sequence works. We have to draw in the inclusions. Okay, so this was called I, this one's called J, this one's called K, and this one's called L. And in the Myvia-Torus sequence, we need to understand the effect of I, J, K, and L in homology groups. Now J, because the homology of V is trivial, there's kind of nothing really to say about this map J, but the map I is kind of is a bit more complicated. Okay, so so the kind of key point is about this I lower star mapping on the effect of this on H1. Okay, so H1 U intersect V, which is ZU, going to H1 of U, which is generated by V and W. So the question is, what's I lower star of U? Okay. So to think about that, we need to let's draw the U in here. Okay, so this is what's happening in our space U, and we've got our U, a little U running all the way around the edge like this. And the homology class of little U is not going to change if we move it, if we distort it slightly, whilst keeping it as a closed loop. And so we can push it out onto the boundary of this square. Okay? As we push down to the boundary of the square, we cover this V, then the W, then V backwards, then W backwards. So U is loop homotopic. Homotopy, so you could move it by a homotopy that it keeps it as a loop the whole time. It doesn't separate the beginning and the end point. V followed by W, followed by V backwards, which we're calling V bar, followed by W bar. Okay. So I lower star of the class represented by U, okay, so it's the same thing because loop homotopy doesn't change the homology class, so it's V star W star V bar star W bar. But we proved quite a while ago that this homology up to boundaries in the homology group, this join operation corresponds to the sum, and the reversal operation corresponds to negation. Okay, so this is the same thing in modulo boundaries. This is the same thing as square bracket v plus square bracket w minus square bracket v minus square bracket w, which is 0. Okay. So our conclusion is that this I lower star map is actually 0 on H1. So let's just record that again. We've got the homology of U intersect V is Z and Z dot U. The homology of U is just Z and then free abelian group on V and W. The homology of V, you've just got a Z in degree 0. And so now we've got a Meyer tori sequence. So let's do it, start from H3, say. Okay, so you've got, and then the same in H2. Okay, and we'll do the truncated version of the Meyer tori sequence because which we can because everything's connected. So we can just put a 0 on the end there. Okay, so what do we know about these? So we know that the homology groups of U intersect V. So we know we've got a ZU here and then nothing in these groups. Homology of U plus the homology of V. So here we know we've got a ZV. We've got V and W here, and nothing from the homology of V. The homology of V is 0 in positive degrees. And then here you've got this H2T. We don't know here H2U and H2V. So again, U has nothing. U has no homology in degree 2 and or higher. So this is all 0. This is all 0 again. Okay, and then we've got this delta map here. Okay, and now this map here. It was I lower star minus J lower star. Okay, now the J lower star bit is kind of mapping into H1V, which is 0 anyway. And then the thing that we said about distorting the loop U, we found that I lower star was 0. So this map here is 0. Okay. Let's get this map was called alpha, and this map here we'll call beta. Okay. Okay, so what do we conclude from this? This sequence has got to be exact. So exactness implies that firstly, you look at this beta here, you've got a 0 on that side and a 0 on this side, so exactness forces beta to be an isomorphism. So that's an isomorphism, which means that H1T is the free abelian group on V and W. So that's one thing, and then we've got this map delta here. Okay, so you've got a 0 coming in on the left, and then a 0 after the delta on the right. So again, that forces delta to be an isomorphism. So that's got to be an isomorphism. So in particular, we see that H2T is isomorphic to Z. And then up here, for the H3, right, you've got an H3 with zeros on either side, and again, exactness therefore forces H3T And similarly, you get HKT is going to be for all k bigger than 2. So here's our conclusion that the homology of torus, standard torus, you get a z, then a z squared, then a z. Okay, so that's one way of doing it. I'll mention quickly an alternative approach. Okay. So S1 is you can use different sets. We can write S1 as the union of open sets like this, with U and V contractible, and U intersect V is an S0. Right? U intersect V is the union of two short intervals like that, so each of those is contractible, so this is a homotopy equivalent to a pair of points. So torus can be written as a union of S1 cross U and S1 cross V, with S1 cross U and S1 cross V are homotopy equivalent to S1, right? Because U is homotopy equivalent to a point, so S1 cross U is homotopy equivalent to S1 cross a point, which is S1. And S1 cross U intersected with S1 cross V that's a homotopy equivalent to a disjoint union of two circles. Okay. So with this approach, it's kind of a bit more difficult to understand exactly how the maps in the Miami torus sequence fit together. But yeah, I'll leave it as an exercise for you to kind of think a bit more about that. I mean, because here, of course, we've got, we do know the homology of all the pieces, right? I mean, the homology of S1 cross U is the same as the homology of S1, which we know. It's the homology of S1 cross V is the homology of S1 that we know. Homology of this intersection is the homology of two copies of S1, which you also know. So when we know all the groups, it's just a question of working out exactly what the maps are. And we get the same answer as before. And the good thing about this approach, although I'm not going to go through all the details of it, is that we can use this to calculate the homology of the n-dimensional torus in the same way as the two-dimensional torus. We can do Tn is the product n-dimensional torus. Is the product of n copies of the circle. T0 is a point, T1 is just the circle, T2 is the normal torus. Okay, so Tn plus 1 is with the same U and V here as Tn cross U union Tn cross V with and of course these are two pieces, Tn cross U, Tn cross V, because U and V are contractible. This is just homotopy equivalent to Tn, and Tn cross U intersected with Tn cross V is homotopy equivalent to Tn cross S0. And what we can conclude from this is it works out that Again, I'm not going to spell out exactly how this works out in the Homology tori sequence, but I'll tell you the conclusion. So the homology of Tn plus 1 is the homology of Tn plus homology of Tn shifted by 1. Okay. So in particular, like the homology of the 3 torus, that's goes the ordinary 2 torus that we've just we discussed previously. That's like so, and then we get the same thing shifted by 1. And so you get this thing with z cubed, z, and then the homology of T4 you get the same thing plus same thing shifted. Okay, so you get z to the 4, z to the 6, z to the 4, z. And you should be recognizing this, or hopefully, as being a binomial coefficient here. So you get 1, 2, 1 there, and then 1, 3, 3, 1, 1, 4, 6, 4, 1. This is all binomial coefficients. And indeed, so by kind of inductive argument based on what I just said, or by various other methods, it's possible to prove that the kth homology of the n torus is a free abelian group of rank equal to binomial coefficient n choose k. So that's all we'll have to say about tori.